Okay, in this practice question, we're asked how far down range a bullet would travel if it's fired horizontally at 300 meters per second, 20 meters off the ground. So, I'm not sure if the question asks about a cliff or a building or something like that, but let's say it's just an elevated height of 20 meters. So if the bullet, or it wouldn't matter if it was a bullet or ball or whatever, it doesn't matter, the projectile is fired at 300 meters per second. Now remember from previous examples is that once it leaves the supporting force, whether it's the edge of the table, cliff, or barrel, it doesn't matter. Once it leaves that supporting force, it will begin to fall. So it's going to fall till it hits the ground. And remember, it's going downrange at the same speed the entire time it's falling. So here it's going 300 meters per second. Here it's going 300 meters per second. And here it's going 300 meters per second downrange. That looks a little scribbly. I hope you can read it. So how far is this distance here? How far away from the base of the cliff or the building does it make it before it hits the ground? Well, the key to this problem is how long did it fall? Because if we know how long it fell, if we get that time, then we will know how long it traveled downrange at this particular speed, and then we can calculate how far that is. Okay, so that's not too terribly difficult. Let's see, we just got to rearrange a formula. That formula that I mentioned previously is distance equals 1/2 times the acceleration due to gravity times the time squared. Now what we're trying to find initially is how long it took to fall and hit the ground. You say, but it was traveling downrange. Won't that affect it? No, it won't, because remember, its horizontal speed and its vertical is completely separate from one another. So the bullet or ball doesn't know that it's going downrange. It thinks it's falling, straight down. It has no idea that it's traveling horizontally at the same time. So it's as if you just dropped it, and we can calculate that time. Now, we want the time here. Now, the way we're going to do that, we're going to use a little algebra, and we're going to divide both sides by 1/2 a, the acceleration due to gravity. Now, why are we going to do this? Because we want the time. And we know if we divide this side by 1/2, that's going to cancel that out. If we divide it by the a, that's going to cancel that out. And what we do to one side, we have to do to the other. So now we have distance divided by 1/2 times the acceleration due to gravity equals the time squared. Now, we don't need the time squared, we just want the time. So we got to undo that square, and the way that we do that is we take the square root of it. So what we do to one side, we have to do to the other. So now we have done a little algebra, and we've rearranged this to equal just the time be the square root of the distance divided by 1/2 times the acceleration due to gravity. Okay, now I'm running out of paper, so I'm going to swap pages here real quick. Don't worry, I'll move that up so you can continue to see it. Maybe. It'll cooperate. There we go. All right. So let's see. In the problem, it told us that the distance was 20 meters. So again, we're trying to find that time. So we're going to say time equals the square root of our distance, which is 20 meters. That's how far it fell. And it did this under the influence of gravity, which is 10 meters per second squared. All right, so let's just take care of this underneath the radical to begin with, okay? And so that's going to be 20 meters divided by 1/2 times 10, which that's 0.5 times 10, so that's going to be 5. So, and that is in meters per second squared. So 20 divided by 5 is 4. So that's going to be 4, and then when you divide a term that has a fraction in it, such as meters per second squared, you're going to invert that and multiply. So ultimately your meters are going to cancel out. Okay, so that's going to leave you in seconds squared. So it's going to be 4 seconds squared. Now, because you're going to take the square root of it, that's going to get rid of the second squared and just leave you in seconds. Hang in there with me. So time now equals the square root of 4, and the square root of 4 is 2. So our time equals 2 seconds. Now we did a lot right there, so let's go back real quick and look and make sure that we understand what we did. Okay, we reorganized distance equals 1/2 AT squared. We reorganized that, so that gave us time equals the square root of distance divided by 1/2 times the acceleration due to gravity. Our problem gave us 20 meters as our distance that it fell, and we divided that by 1/2 times the acceleration due to gravity. Did all our math on that, and that's going to come out to be the square root of 4 seconds squared. Square root of 4 is 2. The square root is going to take care of that guy there, so we'll mark him out. So you're going to wind up with the time equals 2 seconds. Now, we learned in the problem, oh, my computer's shutting down. We learned in the problem that it's traveling 300 meters per second horizontally, and we just solved for the fact that it takes 2 seconds to fall. So if it's traveling down for 2 seconds, that means it's going to be traveling horizontally for 2 seconds as well. So it's going to be falling for 2 seconds, and in the meantime it's going to be traveling downrange, and it's going 300 meters per second. So that's not 25, that's 2 seconds. So if it's going 300 meters per second and it's doing that for 2 seconds, you're going to multiply the 2 times the 3, and that thing should, and the seconds are then going to cancel out, that thing should make it 600, oh sorry, I didn't know you couldn't see that, 600 meters downrange. Because again, we calculate that it fell for 2 seconds and it was traveling downrange those 2 seconds at 300 meters per second. So that equates to 600 meters.